Bernoulli's inequality states that for real numbers x and r, with x positive not equal to 1 and r greater than 1, the quantity x to the r minus 1 is greater than r times x minus 1. Let's see two proofs of this fact. One using differential calculus, that is via tangent lines, and one using integral calculus, that is via areas under curves. Let's start with differential calculus. Let x not equal to 1 be a positive real number, and let r be greater than 1. Consider the graph of the function y equals x to the r minus 1, which is both increasing and concave up as shown here. The derivative of this function is y prime equals r times x to the r minus 1. We can use the derivative to find the slope of the tangent line to y at x equals 1 to be r, so that the equation of the tangent line to y at x equals 1 is r times x minus 1. Now if we take any x value other than 1, we see that plugging the x value into the tangent line results in r times x minus 1, which is less than plugging x into the function, resulting in the quantity x to the r minus 1. Notice that this works for x less than 1 too. The fact that x to the r minus 1 is concave up and increasing means that the curve lies completely above the tangent line. Therefore, we have proved Bernoulli's inequality using differential calculus. Now let's use integral calculus. Again, let x not equal to 1 be a positive real number and let r be greater than 1. But this time, consider the graph of the function y equals r times t to the r minus 1, which is both positive and increasing as shown here. Plugging t equals 1 into the function results in the y value y equals r. First, let's start with an x value greater than 1. We can use this x value to create a region lying above the x-axis and below the curve y equals rt to the r minus 1, between 1 and x. Because the function is increasing, the area of this region is bounded below by the area of the rectangle with height r lying over the interval from 1 to x. But the area under the curve is the integral from 1 to x of rt to the r minus 1 dt, and the area of the rectangle is r times x minus 1. Using the fundamental theorem of calculus, we see that the definite integral is x to the r minus 1, so that we have Bernoulli's inequality in this case. When x is less than 1, we get a similar region lying above the x-axis and below the curve y equals rt to the r minus 1 between x and 1. This time, however, the area of the region is bounded above by the rectangle with height r, lying over the interval from x to 1. This time the area under the curve is the integral from x to 1 of rt to the r minus 1 dt, and the area of the rectangle is r times 1 minus x. We use the fundamental theorem of calculus to compute the integral and see that 1 minus x to the r is less than r times 1 minus x. But if we multiply this inequality by negative 1, we get x to the r minus 1 is greater than r times x minus 1, which is again Bernoulli's inequality. In either case, we got the desired inequality, finishing our proof of Bernoulli's inequality via integration.